Chapter 2. It's not our intelligence. Humans have altered more than 1/3 of the Earth's land surface. We cycle more nitrogen than all other terrestrial life forms combined, and have now altered the flow of 2/3 of the Earth's rivers. Our species uses 100 times more biomass than any large species that has ever lived. If you include our vast herds of domesticated animals, we account for more than 98% of terrestrial vertebrate biomass. Such facts leave little doubt that we are the ecologically dominant species on the planet. Yet they open the question of why us? What explains our species' ecological dominance? What is the secret of our success? To pursue these questions, let's begin by putting aside the hydroelectric dams, mechanized agriculture, and aircraft carriers of the modern world, along with the steel plows, massive tombs, irrigation works, and grand canals of the ancient world. We need to go back long before industrial technology, cities, and farming to understand how a particular tropical primate managed to spread across the globe. Not only did ancient hunter-gatherers expand into most of Earth's terrestrial ecosystems, we probably also contributed to the extinction of much of its megafauna, that is, to the extinction of large vertebrates like mammoths, mastodons, giant deer, woolly rhinos, immense ground sloths, and giant armadillos, as well as some species of elephants, hippos, and lions. While climatic shifts were also likely contributors to these extinctions, the disappearance of many megafaunal species eerily coincides with the arrival of humans on different continents and large islands. For example, before we showed up in Australia around 60,000 years ago, the continent was home to a menagerie of large animals, including 2-ton wombats, immense meat-eating lizards, and leopard-sized marsupial lions. These, along with 55 other megafaunal species, went extinct in the wake of our arrival, resulting in the loss of 88% of Australia's big vertebrates. Tens of thousands of years later, when humans finally arrived in the Americas, 83 genera of megafauna went extinct, including horses, camels, mammoths, giant sloths, lions, and dire wolves, representing a loss of over 75% of the existing megafauna. Similar patterns emerged when humans arrived at different times in Madagascar, New Zealand, and the Caribbean. Sharpening the point, the megafauna of Africa, and to a lesser extent of Eurasia, fared much better, probably because these species had long co-evolved over hundreds of thousands of years with humans, including both our direct ancestors and our evolutionary cousins like the Neanderthals. African and Eurasian megafauna evolved to recognize that while we appear rather unintimidating, and perhaps easy prey given our lack of claws, canines, venom, and speed, we come with a dangerous bag of tricks, including projectiles, spears, poisons, snares, fire, and cooperative social norms that make us a top predator. It's not just the fault of industrialized societies. Our species' ecological impacts have a deep history. Other species have also spread widely and achieved immense ecological success. However, this success has generally occurred by speciation, as natural selection has adapted and specialized organisms to survive in different environments. Ants, for example, capture an equivalent biomass to modern humans, making them the most dominant of terrestrial invertebrates. To accomplish this, ant lineages have split, genetically adapted, and specialized into more than 14,000 different species with vast and complicated sets of genetic adaptations. Meanwhile, humans remain a single species and show relatively little genetic variation, especially when the diverse range of environments we inhabit is considered. We have, for example, much less genetic variation than chimpanzees, and show no signs of splitting into subspecies. By contrast, chimpanzees remain confined to a narrow band of tropical African forest and have already diverged into 3 distinct subspecies. As will become clear in Chapter 3, the manner in which we adapt to diverse environments, and why we thrive in so many different ecologies, does not arise from an array of environment-specific genetic adaptations, as with most species. If not a dizzying array of genetic adaptations, what is the secret of our species' success? Most would agree that it traces, at least in part, to our ability to manufacture locally appropriate tools, weapons, and shelters, as well as to control fire and harness diverse food sources like honey, game, fruit, roots, and nuts. Many researchers also point to our cooperative abilities and diverse forms of social organization. Human hunter-gatherers all cooperate intensively within families, and to some degree on larger scales, ranging from a few families, called bands, to tribes of thousands. These forms of social organization vary on a bewildering array of dimensions, with differing rules for group membership and identity. For example, tribal groups, marriage, for example, cousin marriage, reference Chapter 9, exchange, sharing, ownership, and residence. Just considering hunter-gatherers, our species has more forms of social organization than the rest of the primate order combined. While broadly on target, these observations succeed only in pushing the question back to how and why humans are capable of creating the necessary tools, techniques, and organizational forms to adapt to and thrive in such a diversity of environments. Why can't other animals achieve this? The most common answer is that we are simply more intelligent. We have big brains with ample cognitive processing power and other souped-up mental abilities, for example, greater working memory, that allow us to figure out how to solve problems creatively. The world's leading evolutionary psychologists, for example, have argued that humans evolved improvisational intelligence, which allows us to formulate causal models of how the world works. These models then permit us to devise useful tools, tactics, and stratagems on the fly. In this view, an individual faced with an environmental challenge, say hunting birds, throws his big primate brain into overdrive, figures out that wood can store elastic energy, a causal model, and then goes on to craft bows, arrows, and spring traps to get those birds. An alternative, though perhaps complementary view, is that our big brains are full of genetically endowed cognitive abilities that have emerged via natural selection to solve the most important and recurrent problems faced by our hunter-gatherer ancestors. These problems are often thought of as relating to specific domains, such as finding food, water, mates, and friends, as well as avoiding incest, snakes, and disease. When cued by environmental circumstances, these cognitive mechanisms take in problem-specific information and deliver solutions. The psychologist Steve Pinker, for example, has long argued that we are smarter and more flexible, not because we have fewer instincts than other animals. It is because we have more. This view suggests that since our species has long relied on tracking and hunting, we might have evolved psychological specializations that fire up and endow us with tracking or hunting abilities, as cats have, when we are placed in the right circumstances. A third common approach to explaining our species' ecological dominance focuses on our prosociality, our abilities to cooperate intensively across many different domains and extensively in large groups. Here, the idea is that natural selection made us highly social and cooperative, and then by working together, we conquered the globe. Thus, the three common explanations for our species' ecological success are 1. Generalized intelligence or mental processing power, 2. Specialized mental abilities evolved for survival in the hunter-gatherer environments of our evolutionary past, and/or 3. Cooperative instincts or social intelligence that permit high levels of cooperation. All of these explanatory efforts are elements in building a more complete understanding of human nature. However, as I'll show, none of these approaches can explain our ecological dominance or our species' uniqueness without first recognizing the intense reliance we have on a large body of locally adaptive, culturally transmitted information that no single individual or even group is smart enough to figure out in a lifetime. To understand both human nature and our ecological dominance, we first need to explore how cultural evolution gives rise to complex repertoires of adaptive practices, beliefs, and motivations. In Chapter 3, lost European explorers will teach us about the nature of our vaulted intelligence, cooperative motivations, and specialized mental abilities. However, before setting sail with the explorers, I want to warm up by shaking your confidence on just how smart our species really is relative to other primates. Yes, we are intelligent, as Earth creatures go. Nevertheless, we are not nearly smart enough to account for our immense ecological success. Moreover, while we humans are good at certain cognitive feats, we are not so good at others. Many of both our mental skills and deficiencies can be predicted by recognizing that our brains evolved and expanded in a world in which the crucial selection pressure was our ability to acquire, store, organize, and retransmit an ever-growing body of cultural information. Like natural selection, our cultural learning abilities give rise to dumb processes that can, operating over generations, produce practices that are smarter than any individual or even group. Much of our seeming intelligence actually comes not from raw brain power or a plethora of instincts, but rather from the accumulated repertoire of mental tools, for example, integers, skills, differentiating right from left, concepts, flywheels, and categories, basic color terms, that we inherit culturally from earlier generations. One quick terminological note before we face off against the apes. Throughout this book, social learning refers to any time an individual's learning is influenced by others, and it includes many different kinds of psychological processes. Individual learning refers to situations in which individuals learn by observing or interacting directly with their environment, and can range from calculating the best time to hunt by observing when certain prey emerge, to engaging in trial and error learning with different digging tools. So, individual learning, too, captures many different psychological processes. Thus, the least sophisticated forms of social learning occur simply as a byproduct of being around others and engaging in individual learning. For example, if I hang around you and you use rocks to crack open nuts, then I'm more likely to figure out on my own that rocks can be used to crack open nuts, because I'll tend to be around rocks and nuts more frequently, and can thus more easily make the relevant connections myself. Cultural learning refers to a more sophisticated subclass of social learning abilities in which individuals seek to acquire information from others, often by making inferences about their preferences, goals, beliefs, or strategies, and/or by copying their actions or motor patterns. When discussing humans, I'll generally refer to cultural learning. But with non-humans and our ancient ancestors, I'll call it social learning, since we often aren't sure if their social learning includes any actual cultural learning. Showdown: Apes versus Humans. Let's begin by comparing the mental abilities of humans with two other closely related large-brained apes, chimpanzees and orangutans. As just mentioned, we get smart, in part, by acquiring a vast array of cognitive abilities via cultural learning. Cultural evolution has constructed a developmental world full of tools, experiences, and structured learning opportunities that harness, hone, and extend our mental abilities. This often occurs without anyone's conscious awareness. Consequently, to get a proper comparison with non-humans, it might be misleading to compare apes to fully culturally equipped adults who, for example, know fractions. Since it's probably impossible, and certainly unethical, to raise children without access to these culturally evolved mental tools, researchers often compare toddlers to non-human apes, hereafter just apes. Admittedly, toddlers are already highly cultural beings, but they have had much less time to acquire additional cognitive endowments. For example, knowing right versus left, subtraction, etc., and have had no formal education. In a landmark study, Esther Hermann, Mike Tomasello, and their colleagues at the Institute for Evolutionary Anthropology in Leipzig, Germany, put 106 chimpanzees, 105 German children, and 32 orangutans through a battery of 38 cognitive tests. Their test battery can be broken down into subtests that capture abilities related to space, quantities, causality, and social learning. The space subtest includes tasks related to spatial memory and rotation, in which participants have to recall the location of an object or track an object through a rotational movement. The quantities subtest measures participants' ability to assess relative amounts or to account for additions and subtractions. The causality subtest assesses participants' abilities to use cues related to shape and sound to locate desirable things, as well as their ability to select a tool with the right properties to solve a problem, that is, build a causal model. In the social learning subtest, participants are given opportunities to observe a demonstrator use a hard-to-discover technique to obtain a desirable object, such as extracting some food out of a narrow tube. Participants are then given the same task they just observed and can use what they just saw demonstrated to help them obtain the desired object. On all the subtests of mental abilities, except social learning, there's essentially no difference between chimpanzees and 2.5-year-old humans, despite the fact that the 2.5-year-olds have much larger brains. Orangutans, which have slightly smaller brains than chimpanzees, do a bit worse, but not much worse. Even on the subtest that focused specifically on assessing the causal efficacy of tool properties, causal modeling, the toddlers got 71% correct, the chimps 61%, and the orangutans 63%. Meanwhile, the chimps trounced the toddlers on tool use 74% to 23%. By contrast, for the social learning subtest, averages actually conceal the fact that most of the 2.5-year-olds scored 100% on the test, whereas most of the apes scored 0%. Overall, these findings suggest that the only exceptional cognitive abilities possessed by young children, in comparison to two other great apes, relate to social learning, and not to space, quantities, or causality. Crucially, if we gave this same battery to adult humans, they would blow the roof off the tests, performing at or near the ceiling, 100% correct. This might lead you to think that the whole setup is unfair to the humans, because Esther, Mike, and their colleagues are comparing toddlers to older apes, who varied in ages from 3 to 21 years. Interestingly, however, older apes do not generally do better on these tests than younger apes, quite unlike humans. By age 3, the cognitive performances of chimpanzees and orangutans, at least in these tasks, are about as good as they get. Meanwhile, the young children will experience continuous, and eventually massive, improvements in their cognitive scores over at least the coming 2 decades of their lives. Just how good they will get will depend heavily on where and with whom they grow up. It's important to realize that chimpanzees and orangutans do have some social learning abilities, especially when compared to other animals. But when you have to design a test that is applicable to both apes and humans, the apes inevitably end up near the floor and the humans near the ceiling. In fact, we'll see later that when compared to other apes, humans are prolific, spontaneous, and automatic imitators, even willing to copy seemingly unnecessary or purely stylistic steps. When demonstrations include extra or wasteful steps, chimpanzee social learning emerges as superior to that of humans, because we end up acquiring wasteful or inefficient elements, whereas chimps filter these out. Memory in chimpanzees and undergraduates. Despite the fact that our cognitive abilities improve as we grow up, especially in enriched cultural environments, we still do not end up with uniformly superior mental abilities compared to other apes. Let's consider first the available data comparing humans and chimpanzees in 1. Working memory and information processing speed, and then in 2. Games of strategic conflict. Both sets of findings bring into question the notion that our success as a species results from sheer brain power or better mental processors. The second set of findings questions the notion that our minds are specialized for social maneuvering or strategizing in a Machiavellian world. If you take an intelligence test, you may hear a list of numbers and then be asked to recall those numbers in reverse order. This measures your working memory. Working memory, along with information processing speed, are often considered 2 of the foundations of intelligence. Evidence indicates that greater informational processing speeds and working memory scores are associated with better problem solving and inductive reasoning, called fluid intelligence. Children and adolescents with greater working memory and information processing speed scores at one age tend to have better problem-solving and reasoning abilities at later ages. Since working memory uses the neocortex, and humans have much larger neocortices than chimpanzees, we might expect adult humans to significantly outperform any chimpanzees in head-to-head competition. 2 Japanese researchers, Sana Inoue and Tetsuro Matsuzawa, set up just such a chimp versus human showdown. They trained 3 mother-offspring pairs of chimpanzees to identify numerals on a touchscreen and to tap them in order from 1 to 9. To test processing speed and working memory, they developed a task in which single digits flashed on the screen and were then covered by white squares. The participants then had to tap on the squares, covering the numerals, in order from 1 to the highest digit. The time the participant had to view the numbers in their screen positions before the white square covered them ranged from 0.65 seconds down to 1/5 of a second. These chimps faced off against university students. For working memory, our species did well. In the easiest task, when 6 digits remained on the screen for a full 0.65 seconds, 7 of the 12 humans beat all the chimpanzees, even their star, the 5-year-old Ayumu. On average, the humans tied Ayumu and handily beat the other chimps. And the tie is a bit deceptive, since the human score was dragged down by a weak, missing link, who got only a little over 30% of the sequences correct, making him worse than all the young chimps. However, when the numeral flashes got quicker and the task got tougher, Ayumu beat all the humans. Interestingly, as the flash of numbers sped up, Ayumu's performance remained consistent, whereas the human's performance, as well as that of the other chimps, rapidly degraded. For informational processing speeds, which is the time from the end of the flash until the participant hits his first white square, the chimpanzees ruled. Every chimpanzee was faster than every human, and their speed did not vary with their performance. By contrast, faster human responses tended to be less accurate. Typically, at this point, humans start making excuses for their uneven performance, arguing that the playing field was not level. For example, performances by chimpanzees were measured by their last 100 rounds after 400 rounds of practice. Human scores, however, were based on 50 rounds with no practice. Subsequent work indicates that university students, in fact, can be trained to tie or beat Ayumu in accuracy. However, such excuses can go both ways. The human team was stacked with young, educated adults who were likely at their human peak of working memory and processing speed. If the chimp team had a complex communicative repertoire, like humans, they would no doubt call for a rematch against 5-year-old children to match the ages of the young chimpanzees. The young chimps, who actually outperformed their mothers, would probably defeat any group of young kids. They'd also charge that the humans had a lifetime of experience with the bizarre Arabic numerals that they were forced to learn while in captivity. This dispute can go on and can't be resolved with the existing data. However, the point stands that the humans did not obviously dominate their fellow apes on either working memory or information processing speed, despite our much larger brains. Based on this evidence, it would seem hard to argue that our species' ecological dominance can be readily traced to our dazzling working memory or raw information processing speeds. The true Machiavellians. Now let's consider strategic conflict. We are a highly social species, so perhaps our global dominance has its origins in our social intelligence. One leading view on which selection pressures drove the expansion of human brains and created our fancy mental abilities is called the Machiavellian intelligence hypothesis. This view emphasizes that our brains and intelligence are specialized for dealing with other people, and argues that our brain size and intelligence arose from an arms race in which individuals competed in an ever-escalating battle of wits to strategically manipulate, trick, exploit, and deceive each other. If this is so, we should be particularly good in games of strategic conflict compared to chimpanzees. Matching pennies is a classic game of strategic conflict that has been played with both chimpanzees and humans. In the game, individuals are paired with another of their species for several rounds of interaction. Each player is placed into the role of either the matcher or the mismatcher. In each round, participants must select either left or right. The matcher gets a reward only when his choice, left or right, matches the choice of his opponent. By contrast, the mismatcher gets a reward only when his choice mismatches his opponent. The rewards, however, need not be symmetric. In an asymmetric version, the matcher gets 4 apple cubes, or cash for humans, when she successfully matches on left, but only gets 1 cube when she matches on right. Meanwhile, the mismatcher gets only 2 cubes for any successful mismatches, no matter how they arise. This kind of interaction can be analyzed using game theory. To win, the first thing to realize is that both players should be as unpredictable as possible. Nothing about your prior choices should allow your opponent to anticipate your next play. You have to randomize. To see this, put yourself into the shoes of the matcher. Your opponent gets 2 cubes whether he plays left, L, or right, R. So you should essentially flip a coin with heads for R and tails for L. This means you'll play R and L each 50% of the time, and your opponent won't be able to predict your choices. If you deviate from 50%, your opponent will be able to exploit you more frequently. Now consider matters from the position of the mismatcher. If you now similarly flip a coin, the matcher will shift to play mostly L, since that gives him 4 instead of 1. To compensate, as a mismatcher, you need to play R 80% of the time. Thus, the predicted winning strategy in a contest of intelligent, rational actors is that matchers should randomize their responses, playing L 50% of the time, while mismatchers should randomize by playing L only 20% of the time. This outcome is called the Nash equilibrium. The fraction of the time that one should play L can be moved around by simply changing the payoffs for matching or mismatching on L or R. A research team from Caltech and Kyoto University tested 6 chimpanzees and 2 groups of human adults, Japanese undergraduates and Africans from Busu in the Republic of Guinea. When chimpanzees played this asymmetric variant of matching pennies, they zoomed right in on the predicted result, the Nash equilibrium. Humans, however, systematically and consistently missed the rational predictions, with mismatchers performing particularly poorly. This deviation from rationality, though it was in line with many prior tests of human rationality, was nearly 7 times greater than the chimpanzee's deviation. Moreover, detailed analyses of the patterns of responses over many rounds of play show that the chimps responded more quickly to both their opponent's recent moves and to changes in their payoffs, that is, when they switch from playing the matcher to the mismatcher. Chimpanzees seem to be better at individual learning and strategic anticipation, at least in this game. The performance of the apes in this setup was no fluke. The Caltech Kyoto team also ran 2 other versions of the game, each with different payoffs. In both versions, the chimps zeroed in on the Nash equilibrium as it moved around from game to game. This means that chimps can develop what game theorists call a mixed strategy, which requires them to randomize their behavior around a certain probability. Humans, however, often struggle with this. A final insight into the human's poor performance comes from an analysis of participants' response times, which measures the time from the start of a round until the player selects his move. For both species, mismatchers took longer than matchers. However, the humans took much longer than the chimps. It's as if the humans were struggling to inhibit or suppress an automatic reaction. This pattern may reflect a broader bug in human cognition, our automatic and unconscious tendency to imitate, to match. In matching pennies and other games like rock, paper, scissors, one player often accidentally reveals his or her choice a split second before the other player. This flash look at an opponent's move could result in more victories for those who delay. And in matching pennies, experiments show that it does for matchers, for whom copying leads to victories. For mismatchers, however, it leads to more losses, because they sometimes fail to inhibit imitation. In rock, paper, scissors, it results in more ties, for example, rock, rock, because the slower player sometimes unconsciously imitates the choice of his or her opponent. The reason is that we humans are rather inclined to copy, spontaneously, automatically, and often unconsciously. Chimpanzees don't appear to suffer from this cognitive bug, at least not nearly to the same degree. This is really just the beginning. So far, I have highlighted comparisons between human and ape cognition to suggest that although we are an intelligent species, we are not nearly smart enough to account for our species' ecological success. I could have also tapped the vast literature in psychology and economics, which tests the judgment and decision-making of undergraduates against benchmarks from statistics, probability, logic, and rationality. In many contexts, but not all, we humans make systemic logical errors, see illusory correlations, misattribute causal forces to random processes, and give equal weight to small and large samples. Not only do humans often fall systematically short of these standard benchmarks, we actually often don't do appreciably better than other species, like birds, bees, and rodents, on these tests. Sometimes we do worse. We, for example, suffer from the gambler's fallacy, concord or sunk cost fallacy, and hot hand fallacy, among others. Gamblers believe they are due at the craps tables. They're not. Moviegoers continue watching painfully bad movies even if they know they'd have more fun doing something else, for example, sleeping. And basketball bettors see certain players get the hot hand, even when they are actually seeing lucky streaks that are consistent with the player's typical scoring percentage. Meanwhile, rats, pigeons, and other species don't suffer from such reasoning fallacies, and consequently often make the more profitable choices in analogous situations. If our species is such a bunch of dimwits, how can we explain our species' success? And why do we seem so smart? I'll answer these questions in the next 15 chapters. But before we get to all that, let's put my claims to the test. Stripped of our cultural know-how, can we humans fire up our big brains and stoke up our fancy intellects enough to survive as hunter-gatherers?